Hello, ladies and gentlemen. My name is Jerzy Baranowski, and I wanted to welcome you to a new lecture considering probabilistic computation. In this lecture, which might be split into two parts, we will consider the problem of Monte Carlo sampling. So we start with the most basic idea of sampling, and then we will be building on that to more advanced methods. For start, we will be this lecture should happen some time ago, but because of multiple problems, it should be actually considered a part of lecture number 3, and that's the way it will be positioned on the third playlist on the channel. Okay, so without further ado, let us consider the problem. Generally, what we need to get, in case of Monte Carlo computation, we need to get some kind of way of obtaining random samples from certain distributions. And in order to do so, we need to find a way to get those samples reliable. And generally, we have two options. The option number one is to create random numbers using some kind of hardware generator. And this idea was popular for some time, that generally certain electronic systems will generate, for example, heat or voltages or some kind of other physical phenomena that behaves rather randomly or approximately randomly, and we can sample it using the some kind of analog to digital conversion. Usually we use the we transfer the physical phenomena into voltage. This voltage is being fed to an analog to digital converter, and we get a sequence of numbers that are behaving randomly. And these ideas are realized, for example, using certain diodes or certain resistors with appropriate thermal properties, all stuff like that. And they can be either used with some kind of measuring system, or they can be even created as a peripheral card that you can plug into your computer. So the problem with hardware generators is that they are costly. They are not aging that well, because some methods, some of the phenomena that are behaving in the circuit can be based on let's say age with use. So for example, if we are relying on a thermal phenomena, after some time of use, this thermal phenomena can start behaving differently, for example, through the aging of electrical elements. So in practice, we have to limit ourselves to pseudo-random number generators. Pseudo-random is that we will be able to generate numbers that behave approximately randomly using our computer. So this is a software problem, and generally, pseudo-random number generator is a formula for generating a sequence of numbers, and this sequence of numbers should behave in a way that this sequence should have a low autocorrelation, so it shouldn't be easy to recover previous samples from the current ones as a long period, so it won't be a situation when this sequence will return to its previous position, and also uniformly distributes quantiles of generated numbers. So numbers generated should be generally uniformly distributed. So that would be a good situation. And for many years, the simplest way actually of constructing a random number generator is so-called linear congruent recurrence, which is based on modulo operation of using linear combination of a previous sample and some kind of constant and computing modulo operation. It works, of course, on integer numbers. So those integers are being so our random numbers are generated as a sequence of integers. And in case of those, in case of recurrences, the main aspects are a starting point and the parameters. And of course, the question of those parameters is that usually there are some kind of prime numbers, and because of that, we want to have problems of finding multiple divisors of computation. So our modulo operation wouldn't reduce to zero, and we'll get new integers in answers. And currently, the widely adapted algorithm that is in most of the systems of computing system is Mercenary twister algorithm, which is based on the Mercenary prime numbers, and it's generally it can generate a very long sequences of to few thousand samples, to the few thousand power samples. So it's very low periodic and generally very efficient for Monte Carlo computation. It is not the best algorithm currently available. There are multiple algorithms available. NumPy offers free algorithms to use, but it's popular in many aspects. In many systems as a default generator. This is, however, not so-called cryptologically safe generator because it cannot be used for cryptologic computation. It cannot be used to ensure safety of coding, and for that purpose are different generators. However, we are not really interested in them that much, so we won't be considering. So, having a random number generator, which is a function that you can find in your computer, you initialize it with seed, so defining the initial point, set its parameters. Of course, those things are already being done for you. So, unless you want to enforce the same starting point, you want the generator will provide you examples. Ensuring seed is a good idea in general because it allows you reproducibility of your computation, and we are doing it on laboratories. So, having that, if we have a sequence of numbers, usually integers in certain intervals, we can easily transfer those numbers into a 0-1 interval. A 0-1 interval because we can divide those integers by the largest. And why is that? Because that will give us the possibility to generate probabilities. Because let's get some probability preliminaries for each of probability distribution defined on one-dimensional space, because today we will focus on one-dimensional computation. And for each distribution and for each point, we can define such interval. That's its left end is the minimal possible value, and right hand is the actual value that belongs to this probability this space, and this interval has a probability p of pi, and this interval, that's much better. This probability is, of course, encoded in the cumulative distribution function, which maps each point to the probability of such interval. So the interval from minimal to the x value. And this is, of course, basic knowledge from probability. We are, however, interested in the quantile function, which is, for most practical applications, just an inverse of cumulative distribution function. Why I'm saying that? Because if quantile distribution function is not continuous, and it doesn't have to, it is not invertible directly. You have to do certain tricks, but generally it's a function that maps from the probability, it maps to the right end of the interval that has such probability. So and this quantile function is useful for us because we can use it to generate samples from our uniform distribution, which we obtain from random number generators. Just in one dimension, of course, when we generate a sequence of those uniformly distributed numbers that are constrained to 0 and 1, if we evaluate the quantile functions in each of those points, we get a sequence of points that is a sample from our original pi distribution. So by using feeding quantile functions our randomly distributed, uniformly distributed numbers from 0 and interval, we will get this sequence of samples from pi distribution. And that's the general idea of simple random number generation in one dimension. And that's what we'll be focusing on. And this is useful for us because we can construct so-called Monte Carlo estimators. And Monte Carlo estimators is generally expectation of certain function values. So having the samples from the distribution and having a function that is real valued and integrable, so we can construct an estimator that generally says that an average of values of that function in those samples asymptotically, with the increasing number of samples, tends to the expectation of that function value on the random variable defined by pi. So generally, taking if we have a function defined on our random variable, we can estimate its expectation as an average of values of samples of values of that function taken in the samples from our original distribution. And this is, of course, asymptotically Cal consistency. So as long as n is large, it will be generally good. Of course, for practical purposes, we don't have the n tending to infinity, but if there are certain properties of this distribution and this function, we have some kind of pre-asymptotic convergency, and this function behaves properly. It's more details on that are in the extra reading that you can you will see at the end of this. So what is interesting is that our estimator is approximately normally distributed. So that means that the this random variable, because our estimator is generally a random variable, is a function of a set of random variables, is distributed as its values are taken from a normal distribution, with the mean at the actual expectation of the function, and the standard error given by the square root of the variance of considered function on the probability distribution divided by the n. And this is generally a central limit theorem for Monte Carlo estimators, because if n is sufficiently large and n greater than 10 is practically sufficiently large, and we usually working on much more samples, then this distribution is getting then we can quantify the error of our estimation using this normal approximation. So we have this probabilistic standard error of our function evaluation. So generally, it says that if we want to estimate the function value using samples from distribution, then we can expect that it will be approximating the expected value of that function with a standard error normally distributed. And this is very advantageous situation because of that we are able to estimate the uncertainty that is introduced by Monte Carlo. And MCSE, so Monte Carlo standard error, is a measure of absolute error, which can be even computed directly from the sample. That is a sample of function values, because it can be estimated as a square root of the estimated variance, and then of course estimated variance is can be computed with this estimator. And there's one thing, however, this is absolute error. Absolute error can be very useful in multiple situations because it's most on the scale of comparable to the mean of our function. However, if we are interested in small values of expectation, then we need to consider the relative error, and this relative error might be more, but generally it's very simple, computed just the MCSE estimate of MCSE divided by the estimate of the by the mean of the sample, but it can create certain issues which we see in a moment. So generally, using this this formula, we can construct the requirement. Or we can, let's say, get a bound of how many samples we need in order to obtain the desired relative errors. And this, of course, is relatively simple, but by using this division, if we have desired relative error of alpha, by simple operations, we can see that we need to get a number of samples in the entire process greater than the fraction of having the variance in the numerator and alpha squared and mean squared in the denominator. What is important, if we have requirement of a low relative error, and generally that error will be a fraction either way, because we want it in single persons, or so like 5% or something like that. It will always be less than 1, so it will increase the number of samples. And that leads us to the issue of summarizing our sample, because having those samples, we want to get some kind of representation of them in order to construct those functions that allow us to quantify the phenomena of it. And for that, we have multiple options. The most basic, of course, are moments and cumulants. Moments are things like mean, standard variance, skewness, kurtosis, etc. like that. And further, those we don't have names. But there are also cumulants that are more popular, for example, in physics, which are partially overlap with moments, but generally it's some kind of the integral operation on the distribution, or otherwise it can be an expectation of several functions. So this is of course very easy because we just use it by computing necessary statistics from the sample. That is not very difficult. Different quantity that we are very often interested in is our probabilities, because we really want to know of how we don't want to know the probability, for example, of how the function, how probable is that the function will be located in central interval. For example, what's the probability of function exceeding the desired threshold? And this is the value. This is important, especially if our function is, for example, some kind of utility. Our utility might be economic gain, or it might be constant violation or something like that. And having this utility function, we want to, for example, we want to earn at least 100 zloty per sale, and for that we want to estimate the probability of earning less than that. And how we do it? We reformulate the problem by computing the expectation, which is natural formalism of Monte Carlo computation, by calculating the expectation of the indicator function. And what is indicator function? Indicator function is a function that for certain interval, this here marked as delta f, it gives 1 if our function is in this interval and 0 outside of it. So it's just a simple, like a window function. And it is useful because it's very easily its expectation can be very easily estimated using samples, and it generally reduces to the fact that this probability can be estimated as a fraction of number of samples, or the proportion of samples lying in the interval to the number of samples in total. So, like, generally typical frequency definition of probability, but we got it from different situations. So how many cases are supporting our event? Because our event is function value located in it. And what is useful is that we really can relatively easily estimate the uncertainty of our probability estimates, because Monte Carlo standard error can be relatively easy to determine, and it comes from the fact that the square of the indicator function is equal to the indicator function by itself. So using standard formula for the variance, we can see that transformation becomes very, very easy, as the expectation of the expectation of the square of function is the same as expectation of its function by itself, which is then reduced by square of it. So very simple transformation shows that the variance is the, in a sense, product of probability of the event multiplied by the probability of the opposing event. So the event, the function not being value not being located in the considered interval by the indicator function. And that has, of course, leads us to the MCSE and the relative error. And while absolute error, of course, is less and less as certain we are our probability. So if our probability is 0, of course, some Monte Carlo standard error is 0, and if the standard error is unity, it, of course, is also 0. However, if we consider relative error, so we want to have the how our estimate is similar to our value, then we have an issue that our relative error is increasing with decreasing estimated probability, because as you can see, we have p in the denominator. So if probability of an event is very small, we have a lot of uncertainty, because when it's small, then our relative errors can be relatively large, especially for smaller samples. In order to obtain small relative errors, for example, we want to get the probability of 1%, we'll consider probability 1%, to get the relative error of 5% of that. So to be certain that on 67% in our computation, the probability lies between 1 and 500 of percent in this area, then we have to compute, even using the same formula as before, obtained from the probability estimate. We need to get the 5% errors, we need almost 40,000 samples. And 40,000 samples is generally a loss. So that gives us the intuition that small, low probable events might have lots of sensitivity in them. So estimating them might be difficult, which kind of fits with our intuition. Natural consequence of probability estimate is the histogram, because histogram is the visualization technique that allows us to kind of summarize the entire distribution. And in a way, histogram is the task of probability estimation done for each entire space split into intervals. So using our just considered probability estimate, we can estimate the histogram. Because generally what should be noted that when we are getting our histogram as a sample from certain distribution, then our histogram is not a true value, it's just a certain, there is an uncertainty in that histogram. The uncertainty of our distribution is located inside the error bars of our histogram, not by, the histogram is not a guarantee by itself. And the entire analysis worked like before, so the little bins of low probabilities in our histogram might be uncertain if there are not enough samples. However, it should be noted that in histograms, we generally have few possible types of normalization, because natural histogram is just counts. We count the values or the number of values of the function located inside a bin. Bins are, entire space is divided into bins, so it's divided into conducting intervals, which we can then consider how many points are located in interval. And without normalization, we just get counts. The less popular but easier to interpret version is the count divided by the number of total samples, which gives us each bar of the histogram is an probability estimate of value of a function being located in certain bin. It kind of transforms our distribution into a probability mass function that kind of discretizes our continuous probability distribution into sequence of possible events. And this is really easily interpretable because it's obvious that what we mean, that we just are interested in the advice of how probable is for the function to be located in an interval. The third normalization, the density kind of normalization that you can find, for example, in all the Python functions, is that it divides the histogram in a way that will allow its integral to be equal to 1. So it kind of can be compared with an analytical formula for probability distribution. And it can be easily done by getting our probability histogram, so the histogram that gives probability estimators, and dividing each of those bin heights and also uncertainties by the width of the histogram of the bin. So this division gives us the situation that we have now the possibility of getting it can be compared with probability distribution obtained by analytical. And accompanying the histogram is something called empirical cumulative distribution function, and also known as ECDF. And ECDF is a function that is actually the easiest to explain with code than with formulas, because what we want here is that we want to estimate the cumulative distribution functions using samples, and ECDFs generally do that. Instead of getting bins, it kind of assigns probabilities to each of the samples. So getting values from our we just sort our samples, then we count the number of unique samples. If we have the continuous distribution, usually each of them will be unique, but sometimes it is possible to get two samples of some kind due to rounding errors or just blind luck, because generally we still are sampling over doubles, which have limits. So it's theoretically possible to get sampled two numbers in an interval that will be exact. So we just get their individual values and we get their counts. So we count how many each of the samples appears. If they are unique, each of them becomes one. And then we create the value, and this will be our argument of our empirical cumulative returns. All those unique values and those sorted values, and those values are assigned probabilities that are obtained just by getting the division of how many certain function value like for each function, the value for each value of x, we assign the probability, which is a number of all samples that are equal to this one or less than it, and this is divided by total number of samples. So we just assign the probability of happening at this one or smaller than this one. And we do it by using NumPy functions here. First one is unique, which is just returns the unique values of given given function, and then with appropriate flag, it returns the numbers of those unique values. Then we just use the function cumulative sum, which just at first is the first element, then is cumulative sum of x is vector of x, x1 plus the next element is x1 plus x2, then we have x1 plus x2 plus x3, and all that. So like an integral, getting value after value. So getting those sums here, it just, because we are working on integers, number of counts, we just get the number of counts of value having like this one or less than it, and we divide it by the number of samples to get probability. And this is a basic ECDF that you can find everywhere. Usually, there are some ECDF implementations in statistical packages in Python, but most people wrote them themselves just to know what they are using, and it's often used in multiple courses, for example, data. However, this version does not consider the Monte Carlo standard error, which are actually very simple, because it is the Monte Carlo standard error of probability for the interval from minimal value to the actual value we are considering now. So this is just the variance divided by number of samples for each of those. So like the formula for probabilities stays the same. We can compute it using from props. So it will be square root of actual value probability times 1 minus the probability divided by n. So we will get the Monte Carlo standard errors directly from the vector of props. Okay. And finally, last thing that we are using, and we are using it extensively in all kinds of analysis, are quantiles. Quantiles is an inverse problem to the probability interval problem. It's finding the value set of p that is determines the interval split of the entire probability distribution from minimal value to that value to the the rest. So if we want a p quantile is finding a number that, for example, if we want 27% quantile, we want to find a function value yp that splits our probability distribution into the areas of probabilities 27% and 73%. So getting those this bit. So this is the most known, of course, is the median, which splits the entire distribution in half with respect to areas. And in case of samples, there's one issue, because when we have samples, we have the values, if actually we have the numbers of points that is exactly corresponding to those probabilities, then it's great. For example, for an odd number of samples, we can easily find a median as a middle point of the vector, of the sorted vector, and this is very simple. However, in case if we don't have such situation, we need to kind of, in a way, assign such numbers. And usually it is being done with interpolation. So we want to find a value of x, of value fx between fxn and fxn plus 1, where xn and xn plus 1 are probabilities that are higher and lower than p. So we want to get the value between them, and we use using interpolation for that. You can say that interpolation introduces some errors, but we don't worry about that, because if we have a lot of samples, the interpolation errors will be very small, especially in comparison to Monte Carlo standard error, for which we again require a lot of samples to obtain low relative errors, because we still have the same mechanism for the Monte Carlo standard error of those computations. So generally, using our Monte Carlo estimator, we are estimating either moments and cumulants, or histograms, or probabilities, or ACDFs, or quantiles. So getting some kind of value, numerical representation of value, which will have certain uncertainty coming from Monte Carlo computation by itself. And in case of probability estimates, it will be a compounded situation, that we have an uncertainty from the distribution and uncertainty from the Monte Carlo. So a lot of samples, of course, improves such situation, but we will analyze it with multiple examples in order to get the idea what's going on. We will be, in most cases, we will be sampling 1,000 samples from distributions. We will start with the normal distribution. So from NumPy random, we can import the normal function, and the standard t is not really needed here, so we can drop it at the moment, we need it later. So we just sample normal distribution. We get the as we wanted, as distribution from, or with a mean of 1, and the standard deviation of 1.25. And to do it, we just use the appropriately imported function. So this is very simple. And as we can consider the rolling mean. Code, generally in these slides, I won't be describing code too much. You can find all the code in the Jupyter notebook here, so they are just shown as skipped slides in the Rise.js plugin. So when you import it to Jupyter, you will see all the if you just get it from the repository, you will get all the functions. In this case, we are just creating an image that presents a rolling or otherwise known as expanding means and standard deviations, because we are getting our Monte Carlo estimator of, in this case, an expectation of our normal distribution by getting samples, and in the middle we have the mean, and we've added additionally 1, 2, and 3 Monte Carlo standard errors. So we have the estimate of our value, which we have in the our confidence interval that comes from the Monte Carlo standard error. So as we can see, as long as we are increasing sample size, we are dropping in our we have a reduction of uncertainty. And as we can see on a histogram, when we get a normal histogram, now we can see that there is some uncertainty. As you can see here, we have the histogram that each of the bins is provided with an estimate of its standard error, and as you can see, it can be a bit large sometimes because the variance, of course, will be increasing in the middle, and the division by n won't necessarily be all that helpful, and so the variance is being increased in the so getting that, the histogram can be compared, of course, with the analytical result, which requires extra scaling. So we are just dividing the bin probabilities by the bin width, and as you can see, there is some consistency. Those samples with normal distribution, and it generally fits the standard errors as we do. What's the problem with the histogram is that the width of the bin introduces additional problems, and having the same sample size, we can introduce different kinds of binning. And if the binning will be coarse, which looks less than normal distribution, if it's standard binning, then it will look more or less as the normal one. And if we do too much fine binning, we get a lot of noise because the probabilities of certain values will be very uncertain, because the chance of getting into multiple samples to a bin will be difficult to obtain. So all the probabilities will be not very reliable. So depending on the binning, we'll get different results. So selection of appropriate binning might be a problem. Of course, there are certain automated ways, but it might be useful to consider some expert knowledge regarding the considered distribution that we are working with. For example, if our values are in integers, the bins should be integer related and not introducing certain splits or grouping multiple integers together, while others are separate. As the same situation can be seen with the ECDF. In ECDF, we start with low probabilities with relatively small standard errors, and then we get to the middle when the errors are being increased, which are again dropping dropping when we are approaching to 1. So it looks like a typical normal distribution cumulative distribution function. So this is obviously rather easy. Okay, so this was a very simple situation. We just computed the expectations of the normal probability distribution. So we generally have not pushed it through any function. Now we can do it with the something else. So we will be considering the xpit function, so the inverse logit, that just transforms the real axis into the 0-1 interval. So providing our function with the taking access from real numbers, like from normal distribution, we can get reals, will get when transformed into a 0-1 interval, which your xpit function, of course, can be found, for example, in this SciPy special mode. And it can, as it can be was expected, this situation is very similar. While our samples are constrained, which is generally, we have an issue that our error estimates gets outside of the reasonability interval. It's only in the beginning. Later, all these samples are constrained, and the expectation converges to certain value here. So we get the our transformation didn't change the problem of estimation. Histogram around us see that there is a concentration around this expected value that we've seen there. And of course, this histogram is asymmetric because while we took a symmetric histogram of normal functions, we transformed it into a 0-1 interval, and the logistic function has a sigmoidal shape, so it changes. And this is actually an easier way of handling this transformation than with the analytical computation, because in analytical computation you need to compute the functions of random variables, and if you remember correctly, transformation of random changing the random variables requires us to compute Jacobian and compute those Jacobians in the functions. But of course, if such computation is done, we can see that our simulation result is consistent with the analytical push forward, and generally we can always use numerical computation in order to improve our analytical, but to verify our analytical results, just to be sure that we have not made any mistake on board. Here you can see the shape. Because of this introduction of the function, we get the different shape of ECDF, which we have as our space constraint. Our median is moved to the right because our distribution is strongly asymmetric, and we get the values. The median is located here, and most of probability is around these values. At the most, in a sense that the biggest concentration. So, getting that, we can move to something more complicated. And generally, the complications start with heavy tails, because normal distribution is a very, very nice distribution in a way that extreme values are very unlikely. When x rises to high values, the exponent to minus x squared is very, very small number. It doesn't happen in heavy-tailed distribution. In heavy-tailed distributions, generally, one of the definitions is that you get the probability of getting value 2x is greater than getting 2 samples of value of x and less. So getting higher sample is likely, or at least very good. And one of the typical examples of functions of distribution with heavier tails is the student tree probability distribution, which has is parameterized. It can be parameterized with scale and location functions, the same as normal distribution, which we will not be discussing now, but generally you can multiply it by a scale and you can add a value as a location. This is something exactly the same situation that you can do with a normal distribution. However, there is an additional parameter called μ, and this parameter is the number of degrees of freedom, which of course is very funny in a way that we are often interested in a non-integer value of that, and that's certainly is not actual number of degrees of freedom, but the name stays the same. The student distribution is not that horrible if you look at it. This is a constant, so you don't have to interpret that much. It's just x squared divided by the constant up to certain power. What is interesting, if μ approaches infinity, student t distribution becomes a normal distribution. So it's a natural generalization of using the normal distribution, for example, in robust inference, because it can introduce some heavier tails, but still stay rather close to a norm. However, as long as number of degrees of freedom is high, not even far from infinity, but high, there are no problems. The expectation is 0, and the variance is the is given by a number of degrees of freedom. However, when we move with degrees of freedom below 2, problem starts. Between 1 and 2, the variance is infinite. The expectation is still 0. However, for values less than 1 or less, the variance and expectation are undefined. For example, for 1, it is any number can fulfill the expectation, fulfill the definition of expectation. And this case with any number equal to 1 is called the Cauchy distribution, which is being used in multiple Bayesian computations because sometimes we want to use heavier method. So we'll start with the worst case. We start with the Cauchy distribution, which has heavy tails, and we'll see what happens in our estimates. We're going to, of course, we import standard T functions here. Also, this should be Cauchy. It doesn't change anything because it's just a code snippet, but it should look pretty. So we are sampling from the distribution. We just provide it with one number of degrees of freedom, df. Here again we sample 1,000 samples, and this does not look nice. This does not look nice because in case of our estimator, we see these jumps. Those jumps happen because the variance and is unbounded. Also, the mean is not defined. So, having such situation, we see that there is something really wrong, I think, here. But maybe it is just a problem of number of samples. If we increase 10,000 samples, unfortunately, these variances does not, these jumps does not disappear. Those jumps happen because an extreme value was sampled, and it moves the expectation estimator away from this previous value. So that's how this is a problem that can happen here. We won't be investigating histograms and SDFs of this function because they won't be readable. But we can check whether central limit theorem even holds. Because as we remember, we should remember that our Monte Carlo estimator should generally be normally distributed. So we can analyze, we can sample a set, we can get multiple samples from our distribution, so multiple portions of 1,000 samples, for example, and we can estimate how these things happen. So how the estimate of the Monte Carlo estimate divided by Monte Carlo standard error behaves, because it should be located, it should be normally distributed, located in with the mean in the expectation function. So that's what shows us that the central limit theorem holds. But that's not normal. Having such histogram, we can certainly see that this is not approximating normal in any way. We have a two-model distribution which is completely unrepresentative as its mean. And generally it makes sense because our distribution does not have a mean. So that's a problematic situation. But that doesn't make that such distribution, we cannot do anything with such distributions. No, we can. And it is actually, they can be very useful, but we just need to know what we are doing. And for example, we consider probabilities, because probabilities of distributions are actually values that are probabilities of intervals are something that's always well defined, because all those indicator functions, explanation of those indicator functions are always well defined as long as the distribution makes any kind of sense. But generally, it will be always value between 0 and 1 because it's not possible any other way. And getting such interval is give us a certain statistical property. So we just can compute the push forward from our sample set into the into our indicator function. So you are using vectorize in order to easily use lambda function, but you can use for or anything else. And probability, despite working on the Cauchy distribution that generates very extreme samples, behaves very properly, and it locates in, exactly around the analytical result of 25%, because that's the probability of the interval -1, 0 for the Cauchy distribution, which we can verify by constructing a table that along we get both Monte Carlo error and its and mean estimate, which is reasonable. So, having said that, problems with undefined mean variance are problematic when estimating means. They can be, however, still useful when considering more complicated, different functions that we are interested in. Let's move to different case of heavy tails with infinite variance. Both variance and mean are defined. Mean is 0, but the variance is of the distribution infinite. It's for the system that's the distribution that fulfills this assumption is the standard student T distribution with 1.5 degrees of freedom. Those fractions makes this degree of freedom name especially important. So, what happens? The mean is kind of well captured. However, we still have repeated jumps in the uncertainty. When the extreme value comes, which is the consequence of infinite variance, we get those samples here. We get large increases in the uncertainty, and really this is given as a sequence of samples, but reordering them won't change a thing. Depending on how lucky you were, the uncertainty will be bigger or smaller. And when we move to the analysis of the Monte Carlo estimator, we have a bit better situation than the case of when mean was undefined, but the error quantification is not reliable because it behaves drastically different than for the normal case, because normal case is much more concentrated around its mean than the distribution we've seen here, which it's kind of flat on the top. And finally, we can conclude with a student distribution which is well behaved, which is not normal, but it's has 3 degrees of freedom, so it's still not far away from Cauchy, and far away from normal, but we can analyze this situation. And actually here is also, this should be called sample student variance, consistent with everything, and as we can see, we get the Monte Carlo estimator to the actual value of mean equal to 0, and central limit theorem can be empirically confirmed because our estimator behaves properly and is well represented by a normal distribution. So that's a good thing, and we should be happy of that. And shows us really that our probability, the Monte Carlo computation can work with multiple cases. However, we need to be aware of its pitfalls. And the problem that we encountered here with heavy tails is that for certain heavy tail distributions, certain computations just may not make sense. And for situation that we did before, it was easy. We knew the distribution, we knew its properties. We can kind of get more complicated model of our samples, then we'll have might have some issues because we won't know what the tail behavior is. And the one method of quantifying such situation is using some kind of diagnostic tests, and one of the tests is the k-hat analysis, which is based on approximating details of the distribution using so-called generalized parity distribution. Generalized parity distribution is one of the popular distributions, especially in economy, but it works very well to capture different types of heavy tails, because it is parameterized with parameter k, which is here, depending on its value, the function will have either larger or smaller, heavier or lighter tails. And we won't be performing full Bayesian inference of k hat, because that's not something that we are interested in. We are interested in some kind of indicator. Is there a problem or it's not? Especially that we get some samples and we want to know, are those samples reasonable or not, because our estimates are kind of behaving weirdly. So we can use a point estimate of k hat, which was proposed by Zhang and Stevens. The source is in the links later, and also the also we have the code that computes it, and we can fit using our samples. We can fit the k hat estimate for each of tails of the distribution, and generally we have certain technical rules here that can be helpful. That is, if the k hat is greater than 0.7, it is a really problematic situation. It's a problematic situation that those tails will be very heavy, and there will be a problem. But generally, if k hat is less than 0.25, we can try to do some expectation computations of directly from our functions. If it's larger, it might be risky, and for that we can have a function just splits our function into the splits our function in the median, so it gets the tail on the left of median and tail on the right of median by the differences of our absolute differences of values and its median. So it can be used for parity fitting. So this function is very simple. It just splits the function into left and right tails and moves them away from the median, and it's compute the left and right estimates. And for that, we can see that for Cauchy distribution, especially with small sample, we have very large values of k hat, well above 0.7, and that may be a problem. For student t distribution with 1.5 degrees of freedom, we get the k hat of 0.47 symmetrically here, but equal, and that's may put them in the risky situation. So, but if we move to the normal student distribution, then we get very small values of k hat, which for normals can even become negative, and that also helps when analyzing such distribution, because now we know that we can generally safely compute the expectations and rely on the central limit theorem in some kind of. So what we should, my takeaways from this lecture, first of all, Monte Carlo sampling, as long as the distribution is okay, gives you valuable estimates and allows you some kind of error quantification, not only about the probability and the uncertainty of the entire process that we are modeling, but also on the computational side. Any probability estimate is always burdened with some kind of error. So any kind of histogram, we should be aware that histogram is not an absolute truth. The histogram just gives us the, and it's an absolute truth about the data sample. It's not an absolute truth about the distribution. There is uncertainty there, but it can be quantified in different kinds of summarizing methods. For example, kernel estimators, the uncertainty is very hard to find, right? If the distribution, if samples are problematic to get, they are not well representing the our distribution in any other way for infinite number of them, or the distribution is lacking certain moments, like for example, have an infinite variance. This can happen issues that can be diagnosed with k-hat. But of course, always you can compute the probabilities, and probabilities will always work. And this, of course, was working for one dimension. If the theory of Monte Carlo computation works for multiple dimension, the problem of sample generation is problematic, because getting samples from the probability distribution in one dimension is very simple. We see it here. In multiple dimension, we can press different tools, and those tools will be Markov chain Monte Carlo methods, which we'll be discussing on the next videos in a day or two, or in the foreseeable future. What can be read also? This lecture was heavily based on the Rumble in the Ensemble by Michael Bettencourt, who provides very detailed discussion, especially of general theory of sampling and what sampling means. And I'd strongly recommend reading. However, it might be hard for some people. The k-hat estimator is described in work of Zhang and Stevens, which can be found online in the Technometrics journal. And for people interested in the number generation, there's a Mercenary Twister paper which was proposed by Matsumoto and Nishimura, and it was, but it's also well described on Wikipedia, which I can recommend our initial reading. Thank you very much. This lecture was a long one, and unfortunately it won't be split because I have no idea where to split it. So thank you very much and have a nice day.